Proving triangles congruent. So first we're going to start with the side theorem or postulate that really says that if three sides of one triangle are congruent to three sides of another triangle, then the triangles are congruent to each other. Here we're given that GH and KJ are congruent to each other. So we're going to mark those off on our triangle. We're also given that HL and JL are congruent. So we'll mark those off as well using a different set of tick marks. The last thing we're told is that point L is the midpoint of GK. All right. Well, if GK has a midpoint splits it into two congruent pieces. So I can say that GL is congruent to KL. Those segments are congruent because L is our midpoint. So that's using the midpoint theorem. Now we have that the red, the green, and the yellow sides are congruent to one another, which means three sides are congruent. I can say these triangles are congruent by the side postulate. Let's take a look at another one. We have triangle QRS is isosceles. So here's triangle QRS. That's this large triangle here. We're also told that QR and SR are congruent to each other. Okay, so those are congruent. We're told that RT bisects QS. So here's RT and it is bisecting QS. If it is bisecting at point T, that means T is a midpoint. For QS. And that's by our definition of bisector or segment bisector if you want to get technical. All right, so since we now know that those are, that is the midpoint, we know that QT is congruent to ST, and that's like we used before, the midpoint theorem. All right, lastly, what would be really nice to have is if we could say that third side is congruent. Well, RT is congruent to itself because it's the same line. Or line segment. So we can say that RT is congruent to RT, and that's by the reflexive property. Just writing the same thing twice. All right, so we have that the red, the yellow, and the green sides are congruent to each other. That means side is the reason these triangles are congruent. For these next proofs, let's try to use SAS, side angle side, to prove these congruent. So we're given that WX is congruent to YZ. WX is congruent to YZ. Okay. We're also told that WX and ZY are parallel to each other. So parallel means they are running at the same angle. That's why we put those little arrows, or sometimes you'll even see them drawn as triangles, and that's fine. It doesn't really make a difference. Okay, so we know that those two are congruent, so we can use the concept of transversals to help us out here. Our end goal is to prove that WXZ, this triangle, is congruent to YXZ. So these are the two triangles I'm working with here. All right, so we need an angle and we need another side. All right, well, maybe using that transversal concept, we could say if these guys are parallel and I have a transversal running through them, we can say that these two angles are congruent by using alternate interior angles. So we know that alternate interior angles are congruent. So we can say that angle WXZ is congruent to angle XZY. And that's referring to these angles in here. Okay, so we have a side. We have an angle. What would be really nice is to have the side on the other side of the angle. So this side in between. Okay. So we would love to say that XZ is congruent to XZ, and actually we're allowed to say that using the reflexive property. So now that we have a side, the angle in between, and another side, we can use the SA SAS property. And we want to make sure when we're using SAS that we're using the sides that have the angle in between them, which we sure do. We have these two sides and this angle, these two sides and this angle. All right. In the next one, we're told that FG and GH are congruent. FG, GH. We're told that JG bisects angle FGH. FGH is this angle. This is my bisector. Bisectors cut things in half, so that's going to make these two angles congruent. So we can say that angle FGJ is congruent to angle HGJ, and that is by the definition of angle bisector. Okay. All right, so now we can say we have a side and an angle. It'd be really great to have this side. We can say that JG is congruent to JG or GJ, whatever you want to call it. And that is by the reflexive property. All right, so now that we have a side, an angle, and a side, we can say these are congruent by side, angle, side. Next, let's try using ASA, angle, side, angle. So what we're hoping for is to have two angles and the side in between those angles being congruent. All right, so we are told that QS bisects PQR. So angle PQR is this one. QS is a bisector, which should mean that these two angles are congruent. So angle PQS is going to be congruent to angle RQS. And that's because of an angle bisector. So definition of angle bisector. If you just wrote angle bisector, that's fine as well. All right, we're told that PSQ, this angle, is congruent to RSQ, this angle. Okay. And we want to prove that the top triangle and the bottom triangle are congruent. So really we have these two triangles that we're trying to prove are congruent. All right, well, the last thing we really need is the side in between them, right? We have the red angles and the green angles. It'd be really great if we could say that SQ or QS, however you want to say it, is congruent to itself. Well, something congruent to itself, that's the reflexive property. So now I have an angle, a side, an angle. That's going to give us angle, side, angle. Okay, let's take a look at another one. So we have that ZX bisects angle WZY. So that means that these two angles are going to be congruent. Angle WZX is congruent to angle YZX. And that is by the definition of angle bisector. Okay. We actually can use the same theory here. So actually I'm going to just make this a little bit smaller and see if we can squeeze that in. We can use the same concept here to also say that XZ bisects YXW. So that's this angle. So these angles are congruent. So the same reason. So we're just going to kind of piggyback and put them together. That's WXZ is going to be congruent to, let's see, YXZ. Okay. All right. So the same reason. All right, so the next thing we need, we have the blue angles and the green angles. It'd be really great if I could say that the side in between them was congruent, XZ. Well, XZ is going to be congruent to itself because that's the reflexive property. So I have an angle, a side, and an angle, angle, side, angle. All right, for this next, we want to use angle, angle, side, which means we want two angles and then the side that is not in between them. Okay. All right, so we have that angle DAC, that's this angle right here, is congruent to angle BEC. So that's this angle over here. So let's actually make that a little less complicated and we'll just mark them off without all the extra lines. So this angle and this angle are congruent. That's given to us. We're also told that DC, so from here to here, is congruent to BC, from here to here. Oops, terrible line, sorry. Okay, so what would be useful at this point is, since there's kind of a few different triangles we can look at, is to go to what we want to prove. We want to prove that ACD, we want to prove that this is congruent to EBC, or ECB, sorry, ECB. So it might even be helpful to redraw these. We have ADC, and we have triangle EBC. Okay, we said that angle A and angle E are congruent. We said that BC and DC are congruent. So here's BC and DC. Okay, so now we want to see what else do we know. Well, they share this angle, right? They both have angle C. So we can say that angle C is congruent to itself. And when we say something is congruent to itself, that is reflexive. Now I have two angles and a side that is not in between them. So that is angle, angle, side. Had we used AC, which is in between the two angles, then I would have done ASA. But because I'm using DC, which is not in between the two angles, it's not touching both angles, then I'm using AAS. All right. And then let's see, we're given RQ is congruent to ST. RQ is congruent to ST. We're also told they're parallel to each other. Okay, so parallel should kind of be screaming to me. Whoops, there should be a line there. Should kind of scream out to me that I'm thinking like alternate interior or corresponding or something along those lines. That should kind of be an idea to think transversal. Okay. All right, so we want to prove that RUQ, so the triangle on the left, is congruent to the triangle on the right. So we have sides congruent. That's awesome. Well, we want to know, hopefully we're going to do angle, angle, side in this case. So if we're going to do angle, angle, side, we need two angles. All right, well, first of all, we could absolutely say that these two angles, whoops, if I'll draw, are congruent, and that's because they form this little X, which means they are vertical angles. So that is angle RUQ and angle TUS. Those two are congruent to each other. Okay. The last thing we could do, well, we could do it a few ways. We could actually have solved this problem a different way completely, but that's fine. We have our two parallel lines, and then whichever one you want to call our transversal. Okay, this is our transversal here. All right, so we have alternate interior angles. And with alternate interior angles, they are congruent. So I can say that QST is congruent to QST is congruent to RQS. Oh, actually, let's relabel these a little bit more so that makes a little bit more sense. So I know we could start at Q, but we could also call this UST, right? We could start here to here to here. So UST, that way we're keeping to the letter combinations here, is going to be congruent to, let's see, UQR. Okay. All right, and that's by alternate interior. You absolutely could have said that angle R and angle T were congruent to each other as well, and there would be nothing wrong with doing that. Okay. All right, and then last but not least, we could say that these are congruent by angle, angle, side. Though there are multiple ways we could have done this. We could have also done this one by angle, side, angle.